Hi guys, welcome to my YouTube channel. Today we'll see introduction to VLSI and overview of chip design integration techniques. Okay, let's start with a question. Have you ever looked at your super powerful small smartphones and have you ever compared with the bulky cell phones from 10 to 20 years ago or even old landline telephones our grandparents used? These phones were wireless and big, and they are just for a single operation, which is to make calls. When we compare those phones to our phones today, these are very tiny, powerful computers that can take pictures, browse internet, and run thousands of apps. If you see these kind of, if you see the changes, you will get two questions, which are, how did this incredible change happen? How did we pack so much power into small space? The answer to these questions are like integration, which is VLSI, very large scale integration. Okay. In this video, we'll cover four key topics to give you a solid foundation. First, we'll get the answer what is VLSI. Then we look at the evolution of integration levels that lead us to where we are today. After that, we'll give you a high level look at VLSI Design Flow, which is the roadmap of creating chips. Then we'll finally look at various design styles which were used by engineers today. Okay, let's get started. So, what is VLSI? What exactly it means? The full form of VLSI is very large scale integration, which means integration of millions or even billions of transistors on a single integrated circuit or chip. If you see the image, it gives an idea which looks like a complexity of circuits were built on a tiny square of silicon. But we did not get here overnight. VLSI. Before VLSI, the technology evolved through various key stages defined by the number of transistors. The first state is SSI, which is called as small state integration, which means integration of 10 to 100 transistors per chip. Then we'll go to MSI, which means medium scale integration, which means integration of 100 to 1000 transistors on a chip. Next we'll go to LSI, which means 1000 to 10,000 transistors on a chip. Next we will come to the our present state, which is called as VLSI, which means very large scale integration, in which we integrate more than 10,000 transistors on a chip. The next stage will be ULSI, where the transistor count are so massive that exact number is not even clearly defined. Okay, we are packing more transistors on a chip. Why is that so important? There are four huge advantages, which is smaller size. More components in the same space means smaller the final products look like our phone and smartwatch. Lower cost. Manufacturing chips at this scale drastically lowers the cost per function. Next, low power. VLSI allows for incredibly power efficient designs, which is why your device have such a great battery life. And maybe the last and very important one is more functionality in a single device. A single chip can now handle a task that once were require a whole circuit board. This amazing this amazing journey has amazing history. It all began with invention of transistor by Bell Labs, which was which was the foundation for digital electronics in the future. And in 1958, the first integrated circuit was designed by Jack and Robert. Then comes the integration levels, which are in 1960s SSI and MSI. A major breakthrough came in 1971 when Intel released 9, Intel 4004, the first commercial microprocessor with about 2300 transistors. In 70s and 80s belongs to we saw a big shift of uh, from LSI to VLSI, where the design methods were introduced by the pioneers Mend and Conway. This table puts the evolution in perspective. Look at the 404 in 1971. The count of the transistors is 2300, and when we jump to present in 2024, Apple uses the transistor count of 28 billion and or even more also. Okay, the the transistor count and at the same time the technology node, which you can think of size of a component shrank from 10,000 nanometers down to the 5 or 3 nanometers. This relentless shrinking is how we achieve the incredible density in the transistor count set. This incredible progress is perfectly captured by what's known as Moore's law. It is famous observation that number of transistors on a microchip doubles approximately every 2 years while the cost per transistor decreases. This, if you see this graph, you can understand what I'm trying to say. Here, as the years increases, the number of transistors on a chip will be, which is getting increased. This was proposed by Moore. Okay, next. So, how do you manage all this complexity? You follow a very structured process called as VLSI Design Flow. This is like a blueprint or construction plan for a building. It starts with chip specification, what is chip supposed to do, then it goes through the steps like design entry, synthesis and translation design into the tools, and for planning, end route and placement and route, and finally verification to make sure it works well before you give it to the manufacturer. We'll deep dive into these steps in the future videos. Now, when you design a chip, you don't always start from the scratch. There are different approaches you can take. We we call them as design styles. There are three main design styles, which are called as full custom, semi-custom, and gate array technology, or called as FPGA. Let's start with full custom design. In this style, the designer defines exact placement and connection of every transistor. The analogy I would like to use here is like building a house brick by brick. You control everything from the foundation to wiring to paint job. This gives you most freedom and highest possible performance, and but it is also very expensive and time consuming. Next, we have semi custom device design. Here you use pre-designed blocks, which are called as standard cells. Your job is to arrange these blocks and wire them together. Using our house analogy, this is like having a house that is already built, and your job is to just paint it and arrange the arrange the furniture inside. It is much faster and more efficient than than a full custom design, but you can give up some performance flexibilities. Next, when you come to FPGA, think FPGA as a chip that is a blank slate of logic blocks and wires that are already manufactured. Your job as a designer is to purely program the connections between these blocks to create your digital circuit. This is the fastest method to get working prototype, and it is very incredibly flexible because you can reprogram it over and over again. This is like buying a prefabricated home where you can instantly rearrange the walls, wires, with the push of a button. So with these three options, with which one do you choose? It depends on project needs. We have considered several things. You have to consider several things. Your budget. Full custom is most expensive and FPGA is the cheapest to start with. Time you have. FPGAs are fastest, full customs is the slowest. Area efficient. Full custom designs can be made the smallest and more compact, but FPGAs are the largest compared to them. And the flexibility, when it comes to flexibility, which means how much do you control you need over the final performance. And that's our overview on VLSI. We have covered what it is, its history and its advantages and different ways of engineering design these incredible chips. I hope you found this introduction very helpful. If you like the content and you want to see more, please like, share and subscribe to the channel. Thank you so much for watching, and I will see you in the next video.